The smooth roll that would revolutionize automotive performance forever began its first rotation on the test track at Michelin's Clermont-Ferrand facility on June 4, 1946. Marius Mignol, the brilliant tire engineer who had spent years perfecting the radical new construction, felt the revolutionary difference as his prototype radial tire maintained perfect road contact while providing superior handling that no bias-ply tire could match. "Gentlemen, we've just solved the automobile's greatest tire limitation," Mignol announced to the assembled Michelin executives as the experimental Citroën equipped with radial tires demonstrated grip, durability, and fuel economy that seemed impossible with conventional tire technology. For the first time in automotive history, tires can maintain optimal road contact while providing longer life, better handling, and improved fuel efficiency simultaneously. Marius Mignol's radial tire construction represented the first successful solution to automotive tire performance, replacing the primitive bias-ply designs that had limited vehicle capabilities since the automobile's invention. The innovation would transform not just tire technology, but establish the foundation for all modern automotive performance, safety, and efficiency. The engineering achievement was revolutionary. Mignol had created a tire construction that separated structural support from road contact functions, allowing optimal performance in both areas while eliminating the compromises that made bias-ply tires inadequate for modern automotive demands. Most significantly, radial tires would prove to be one of automotive engineering's most fundamental breakthroughs, enabling the development of high-speed highway travel, improved fuel economy, and the precise vehicle handling that defines contemporary automotive performance. If you love discovering the untold stories behind automotive history's most incredible innovations, please like this video and subscribe to the Car Chronicles. 1885–1940, the bias-ply tire limitation. For the first 60 years of automotive history, tire performance remained the weakest link in vehicle design, with bias-ply construction creating fundamental limitations that restricted speed, handling, durability, and fuel economy. Early tires used construction methods borrowed from horse-drawn vehicles that were inadequate for the speeds and loads of automotive operation. Bias-ply tires were constructed with fabric cords running diagonally across the tire at opposing angles, creating a flexible but structurally compromised design. This construction method required the same tire structure to provide both structural support for the vehicle's weight and optimal road contact for traction, resulting in compromises that made both functions less effective. Bias-ply tires were fundamentally compromised by their construction, recalled automotive engineer Charles Kettering. The diagonal cord arrangement meant that structural strength and road contact performance worked against each other. Making tires stronger for load carrying made them worse for handling, while optimizing for road contact reduced their ability to support vehicle weight reliably. The heat buildup problems with bias-ply construction were severe and often dangerous. The flexible sidewalls would flex constantly during operation, generating heat that broke down rubber compounds and caused tire failures. High-speed driving was particularly problematic, as heat buildup could cause catastrophic blowouts that resulted in serious accidents. Fuel economy was negatively affected by bias-ply tire inefficiencies. The constant flexing of tire structures created rolling resistance that required more engine power to maintain speed, reducing fuel efficiency and increasing operating costs for vehicle owners. Handling characteristics were unpredictable and often dangerous with bias-ply tires. The flexible construction would allow tire shapes to distort during cornering, creating inconsistent contact patches that made precise vehicle control difficult. Emergency maneuvers often resulted in tire failure or loss of control. Tire life was disappointingly short with bias-ply construction. The constant flexing and heat generation would cause premature wear and structural failure, requiring frequent tire replacement that made automotive operation expensive and inconvenient. Weather performance was particularly poor with bias-ply tires. Wet road traction was marginal due to inadequate tread design and poor road contact, while cold weather made tires hard and inflexible, further reducing performance and safety. 1930s, the performance crisis. As automotive speeds increased and highway systems developed during the 1930s, the limitations of bias-ply tire construction became increasingly apparent and dangerous. Faster vehicles required tire performance that existing construction methods simply couldn't provide safely or reliably. Highway driving created new demands for sustained high-speed operation that exposed every weakness in bias-ply tire design. Heat buildup, structural fatigue, and handling instability became serious safety concerns as vehicles routinely operated at speeds that pushed bias-ply tires beyond their practical limits. Aircraft tire development was advancing rapidly during this period, as aviation applications demanded superior performance from tire designs. Aircraft engineers were developing construction methods that could handle extreme speeds and loads while maintaining reliability, suggesting that better tire construction was possible with proper engineering. European manufacturers, particularly in France and Germany, began systematic research into improved tire construction methods during the 1930s. These companies understood that tire technology was becoming a limiting factor in automotive performance and competitiveness. The tire industry recognized that bias-ply construction was reaching its practical limits, noted tire industry historian Maurice Mignol. Vehicle performance was advancing rapidly, but tire technology was lagging behind, creating a bottleneck that limited what automobiles could achieve safely and efficiently. Michelin emerged as a leader in advanced tire research, committing significant resources to developing construction methods that could overcome bias-ply limitations while providing the performance characteristics that modern automotive applications required. World War II interrupted civilian tire development, but accelerated military applications that demanded superior performance under extreme conditions. Military experience demonstrated the urgent need for tire technology that could support advanced vehicle performance requirements. The wartime shortage of natural rubber also forced tire manufacturers to develop synthetic rubber compounds and construction methods that would be essential for post-war automotive tire advancement. 1940-1946. Mignol's Engineering Challenge. Marius Mignol joined Michelin's Advanced Tire Development Program in 1940 with specific instructions to overcome the fundamental limitations of bias-ply construction while creating tire designs that could support the high-performance automotive future that engineers envisioned. The challenge facing Mignol was enormous. Create a tire construction that could separate structural support functions from road contact optimization, allowing both areas to be perfected without compromise while remaining practical for mass production and everyday automotive use. Mignol's breakthrough insight came from studying aircraft tire construction and industrial belt systems, which had solved similar problems of combining structural strength with flexible operation. However, automotive applications required different solutions due to the need for long service life, multiple road conditions, and cost-effective manufacturing. The key innovation was Mignol's development of radial construction, where steel belts provided structural support while perpendicular sidewall cords allowed optimal road contact. The radial design separated structural and contact functions, allowing each to be optimized independently. Mignol's radial concept was revolutionary in its approach to tire construction, explained tire engineer André Michelin. Instead of asking one structure to do everything poorly, radial design used different components to do different functions perfectly. Steel belts provided structural integrity while flexible sidewalls maintained optimal road contact. The steel belt construction required innovations in materials and manufacturing that pushed tire technology into new areas. Mignol developed steel cord arrangements that provided tremendous structural strength while allowing the flexibility necessary for road contact optimization. Sidewall engineering was equally critical to radial tire success. Mignol created sidewall designs that could flex for road contact without generating the heat and structural stress that limited bias-ply tire performance and durability. Manufacturing radial tires required completely new production methods and equipment. The complex construction demanded precision assembly and quality control that exceeded anything previously required in tire manufacturing. June 4, 1946, the breakthrough demonstration. Michelin introduced Mignol's radial tire construction on June 4, 1946, using specially equipped test vehicles that could demonstrate the superior performance characteristics of the new design compared to conventional bias-ply tires. The demonstration was immediately convincing. Test vehicles equipped with radial tires showed superior handling, braking, and stability compared to identical vehicles using bias-ply tires. The radial-equipped cars could corner faster, stop shorter, and maintain control under conditions that caused bias-ply tires to lose traction. The difference was obvious to everyone present, recalled automotive journalist Paul Frere. Radial tires provided handling precision and predictability that made bias-ply tires seem primitive by comparison. The improvement in road contact and vehicle control was dramatic and immediate. The durability advantages were equally impressive. Radial tires showed significantly less heat buildup during high-speed operation, while maintaining structural integrity under loads and conditions that would damage bias-ply tires. The separation of structural and contact functions eliminated the compromises that limited bias-ply performance. Fuel economy improvements were measurable and significant. Radial tires reduced rolling resistance by minimizing the flexing losses that made bias-ply tires inefficient, resulting in fuel economy improvements of 5 to 10% depending on driving conditions. Michelin positioned radial tires as fundamental automotive advancement rather than incremental improvement, understanding that the technology represented a completely new approach to tire design that would eventually replace all existing construction methods. Customer response was overwhelmingly positive among those who experienced radial tire performance. The improved handling, longer life, and better fuel economy made radial tires immediately attractive despite higher initial costs compared to bias-ply alternatives. The automotive press recognized radial tires as a genuine breakthrough that would influence vehicle design and performance for decades. Technical publications predicted that radial construction would become the standard for all automotive applications. 1947–1960, European adoption and development. The success of Michelin's radial tires created immediate interest among European automobile manufacturers who recognized that tire technology was becoming a critical factor in vehicle performance and competitiveness. French manufacturers led radial tire adoption, with Citroën becoming the first automaker to offer radial tires as standard equipment on production vehicles. The combination of radial tires with advanced suspension designs gave French cars distinctive handling characteristics that influenced automotive development throughout Europe. German manufacturers embraced radial technology for its engineering sophistication and performance benefits. Companies like Mercedes-Benz and BMW understood that radial tires were essential for the high-performance vehicles they wanted to develop for emerging highway systems. The technology evolved rapidly during European adoption. Michelin developed improved steel belt constructions, better rubber compounds, and manufacturing processes that reduced costs while improving performance. Each generation of radial tires delivered better durability, handling, and efficiency. Racing applications provided proving grounds for radial tire development. European racing circuits demanded extreme performance from tires, leading to innovations in construction, materials, and design that eventually benefited production automotive applications. By 1960, radial tires were standard equipment on most European vehicles and had established clear superiority over bias-ply construction in every measurable performance category. The technology that had seemed exotic in 1946 became fundamental equipment that European customers expected. However, American manufacturers remained largely resistant to radial tire adoption, viewing the technology as expensive and unnecessary for American driving conditions and customer preferences. This resistance would eventually cost American companies significant market position as radial advantages became undeniable. 1970s, American conversion and global adoption. The American automotive industry's resistance to radial tire technology finally collapsed during the 1970s as fuel economy concerns and import competition forced recognition that radial tires provided essential performance advantages that could no longer be ignored. The 1973 oil crisis made fuel economy a critical factor in automotive purchasing decisions. Radial tires, superior rolling resistance, and fuel economy benefits became compelling advantages that American manufacturers and consumers could no longer overlook for cost considerations. Import vehicles equipped with radial tires demonstrated superior handling, durability, and efficiency compared to American vehicles using bias-ply tires. This performance difference contributed to the growing success of European and Japanese vehicles in American markets. American tire manufacturers, led by Goodyear and Firestone, finally committed to radial tire development and production. The conversion required massive investments in new manufacturing equipment and processes, but became essential for competitive survival. By 1975, most new American vehicles were equipped with radial tires as standard equipment. The conversion happened rapidly once it began, as the performance advantages became obvious to manufacturers, dealers, and customers. The global adoption of radial tire technology was completed by 1980, with bias-ply construction surviving only in specialized applications where radial advantages were not critical. Radial tires had become the universal standard for automotive applications worldwide. Contemporary performance and innovation. Modern radial tires are direct descendants of Marius Mignol's 1946 innovation, using the same basic construction principles while incorporating sophisticated improvements in materials, design, and manufacturing that provide performance far beyond early radial capabilities. Advanced materials have revolutionized radial tire construction. High-strength steel belts, synthetic rubber compounds, and computerized tread designs provide performance, durability, and efficiency that early radial tire designers couldn't have imagined while maintaining the fundamental construction principles. Electronic manufacturing controls enable precision construction that ensures consistent performance and quality across millions of tires. Computer-controlled production creates tires with tolerances and uniformity that were impossible with manual manufacturing methods. Specialized radial tire designs serve specific automotive applications. High-performance tires optimize handling and speed capabilities, while eco-friendly designs maximize fuel economy and environmental sustainability. Winter tires use radial construction optimized for cold weather traction and safety. Electric vehicle applications are driving new radial tire development as EVs create unique requirements for low rolling resistance, quiet operation, and durability under different load and torque characteristics compared to conventional vehicles. Racing continues to advance radial tire technology through extreme applications that push materials and construction methods to their limits. Racing innovations in heat management, grip, and durability continue to influence production tire development. Impact and recognition. Marius Mignol's development of radial tire construction represents one of the most important automotive technology innovations in history, transforming vehicle performance while enabling the high-speed, efficient transportation systems that define modern mobility. The technology's safety impact extends beyond performance improvements. Radial tires, superior heat management, structural integrity, and predictable handling characteristics have prevented countless accidents by providing reliable performance under demanding conditions. From an engineering perspective, radial tires established important precedents for separating functional requirements that continue to guide modern automotive technology development. The principle of optimizing different components for specific functions rather than compromising single components for multiple functions influences contemporary automotive design. The economic impact was enormous. Radial tires' superior fuel economy, durability, and performance provided economic benefits that far exceeded their higher initial costs, while enabling automotive designs and highway systems that transformed global transportation and commerce. Environmental benefits from radial tire technology include reduced fuel consumption, longer tire life, and improved vehicle efficiency that reduce automotive environmental impact. Modern, eco-friendly radial designs continue advancing environmental sustainability in transportation. The global transformation from bias-ply to radial construction demonstrates how fundamental engineering breakthroughs can revolutionize entire industries while improving human safety, economy, and environmental sustainability simultaneously. The radial tire revolution that began with Mignol's 1946 innovation reminds us that the most important automotive advances often involve reconsidering fundamental assumptions about how things should work, leading to breakthrough solutions that benefit everyone who drives. If this story moved you, subscribe to the Car Chronicles and hit that like button. Share it with someone who needs to know that the greatest automotive innovations are often the ones that improve performance, safety, and efficiency simultaneously, and that French engineering has repeatedly revolutionized automotive technology in ways that benefit drivers worldwide. What's your most memorable tire experience? Let us know in the comments how radial tire performance has influenced your driving confidence and vehicle capabilities.